Now let us consider the example of conical pendulum. This also we have discussed in one of the previous lectures, I think as problem 2. And here also we want to establish the relationship between torque and rate of change of angular momentum. Okay, so let us consider a conical pendulum. This is the first rod, okay, and this is the vertical direction. This is the second rod, and this is the bob. Okay, so the first rod is revolved like this with an angular velocity omega, and this can be taken as a z-axis. And the second rod is having a length L. Okay, bob has a mass m. So when this first rod is rotated with an angular velocity, the second rod, this is the pivot, second rod is rotated in this horizontal plane, making a circular path. Let us consider this horizontal plane as a xy plane. Okay. Okay. Now let's consider this pivot as point B. This angle let us take as alpha. Consider this center of the circle as point A, and the radius of the circle is R. So this is a conical pendulum. Now first we want to, in the previous problem we have calculated angular momentum of this conical pendulum about both A and B. Okay, first we calculated angular momentum about the point A here, and then we calculated angular momentum about the point B also. Okay, so now what we are going to do is we will calculate the torque acting on this bob about point A, and then we establish the relationship between torque and angular momentum about this origin, and also we calculate torque and calculate torque about this origin, okay, B, point B, and calculate and establish the relationship between torque and angular momentum. So we will show that in both cases, with respect to the both origins A and B, torque can be shown to be equal to rate of change of angular momentum. Okay, so first let us consider choose the origin as point A. Okay, so what is the angular momentum about this origin? Angular momentum about A, this we have calculated in the previous problem. This is okay, m r square omega along the direction k. Okay, you can refer problem 2. R cross mv we have to take, and here mv will be tangential to this circular path at this point. Okay, we just assume that this is revolving in the, when we look from above, suppose it is revolving in the anti-clockwise direction. Okay, so here this will be P will be tangential along this direction. This will be the direction of mv, and the direction of R will be like this. This will be the direction of R. So R cross mv will be, you can see that both R and mv are in the xy plane, so R cross mv will be in the plus z direction, that is Clay direction. So we get and it's in the plus z direction. The magnitude is perpendicular distance to mv, okay, which is perpendicular distance from A to mv is simply R, so R into mv, or mvr, and v is nothing but r omega, so mr square omega along the k direction. That is angular momentum about the point A. And here what we see is that in the previous problem we have noted that this mass is constant, r is constant, omega is constant. So angular momentum about this point should be constant. Okay, about the point A should be constant. Let us calculate the torque. So in order to get the torque, we should know the different forces acting on this mass. So one point most force is the weight mg acting vertically downward, and then tension of this exerted by the rod on the bob of mass m, and this tension will be acting along the direction of the rod. So tension with which the rod pulls the mass. Okay, so these are the two forces acting at the bob, tension and weight. So we can resolve this. We can resolve the tension along the vertical direction. So let me draw it in a better way. Okay. So let us consider tension along the vertical direction will be, if this angle is alpha and this angle is also alpha, so this is T cos alpha, and tension along this direction will be T sin alpha. Okay. So T cos alpha will be along the vertical direction, T sin alpha will be along the horizontal direction towards the center. So in the consider the bob. The bob is undergoing uniform circular motion in the xy plane. Okay, there is no motion of the bob in a perpendicular to the xy plane. There is no upward or downward motion. That means the net force acting in the vertical direction on the bob will be 0. So this T cos alpha upward and weight in the downward direction should balance each other. Okay, so we can write T cos alpha minus mg should be 0. Vertical direction I am taking as positive. Let's call this equation 2. So the only force, only unbalanced force acting on the bob is this T sin alpha, which is acting in the towards the center, right? So that is the only force acting here. So let us calculate the torque due to this force. Okay. So I will draw a separate figure for that to clarify this point. It's the vertical direction, and here is our pendulum bob. Maybe I will draw it like this. This is the radial distance. Okay. So this part is length L alpha, and we know this is the force towards the center. Okay. So in order to get the torque, so we want to calculate the torque about the point A. This is point B. So from the figure, what you see is that torque about point A is r cross f. What is r? R is the radius vector from point A, that is our origin, to the mass m. Okay, this is our mass m, or the radial distance from the origin to the point where the force is acting, right? The perpendicular distance. So sorry, r is the radial vector from the origin to the particle, right? Okay, this torque is from the figure, it is Ra cross F. But from the figure you can see that this R, A and F are along the same line. R, A and F is anti-parallel to each other. The angle between them is 180 degree. So this is nothing but 0. Okay. So if torque is 0, if this is the relationship between torque and angular momentum, torque is equal to rate of change of angular momentum. We know that this is the relationship. Let us see whether this is consistent in this particular case. If tau A is equal to 0, okay, this implies rate of change of angular momentum about this point should be 0, which in turn implies angular momentum about the point is equal to constant. Okay. Now compare this result with equation 1. In equation 1 we have established that angular momentum about the origin A is mr omega square k. Its magnitude as well as direction always remains constant. So about origin, angular momentum is constant and torque is 0. So this is consistent with the result that torque is equal to rate of change of angular momentum. Okay. That's why when torque is 0, angular momentum about origin A is 0. Now let us consider origin B. Okay. So in the next part let us consider origin B. We want to calculate the angular momentum about the origin B. Angular momentum about the origin B, this we have calculated in the previous problem, but let us try it again. The radius vector from origin B to this point is RB, vector RB, and the magnitude of vector RB is same as L. Okay. So in the previous figure I have shown that the direction of linear momentum, this is in the anti-clockwise direction, this rotation. So direction of linear momentum is like this. Okay. So this is RB cross MV, and in this particular geometry RB and MV are perpendicular to each other. So its direction from this figure, direction of RB is along this direction, MV is along this direction. So the direction of angular momentum vector must be perpendicular to both RB and MV. So it is perpendicular to this inclined plane. Let us consider this direction. This is the direction of LB. Okay, and what is the magnitude? The magnitude is MV into L. Okay. So this the magnitude of LB is, the perpendicular distance is RB itself, that is L. So L into MV, capital M into V, and this V is R omega. So we have M R omega L. This was the result that we have obtained earlier. Okay. Okay, we will come back to this result later. Now let us try to look at the torque now. Okay, what is the torque acting on this body? Maybe we should draw another figure. Okay. Is equal to modulus of RB, and RB vector is along this direction. The force is along this direction towards the center. So if we take R cross F, that is the direction of torque, right? So the direction of torque will be along this direction, tangential to the circular path. This will be the direction of torque. Okay, so what is the magnitude of torque? This angle is alpha. What is the magnitude of torque about the point B? This is the point B. So for that we need perpendicular distance from the point B to the position of the body, or perpendicular distance from the point B to the force, right? And this perpendicular distance from the point B to the force is nothing but this distance. Okay, this distance, vertical distance. And how much is this vertical distance? If the length of this rod is L from the pivot B to the mass M, if the length of the rod is L, this part, vertical distance will be L cos alpha. Okay, so the magnitude of torque will be L cos alpha into force. Okay, now what is the force? I think we have calculated it somewhere. Yeah, we have shown it here. What is the force acting on the body? What is this horizontal force towards the center? Its magnitude is T sine alpha. Okay, so let us substitute that here. So this F is equal to T sine alpha. So the magnitude of torque is about the point B is L cos alpha into T sine alpha. Now we can rewrite this using equation 2. In equation 2, we can see that this vertical component T cos alpha, the vertical component of the tension T cos alpha is balanced by the weight mg, or T cos alpha equal to mg. Now in this expression for magnitude of torque, we can combine T and cos alpha. Okay, so from equation 2 we have T cos alpha is equal to mg. Okay, if we substitute that result in the expression for torque about origin B, T cos alpha we can write as mg. So we have mgl into sine alpha. That is the magnitude of torque. Then what is the vector form of torque? mgl sine alpha. We can see that this torque is tangential to the circular path, and this is the direction in which angle theta, the polar angle theta, increases. So we can say that it's the direction theta cap. So this is our next equation, equation 5. Let us keep it here. This is the magnitude of the torque about the origin B. Okay, magnitude of torque about the origin B, and its direction is tangential to the circular path, which is the direction of increase of the angle theta. So mgl sine alpha theta cap. Okay, now our aim is to establish the relationship between torque and rate of change of angular momentum about the point B. Okay, so the rate of change, now we want to calculate what is the rate of change of angular momentum about the point B. Okay, so I will draw a separate figure for that again, otherwise this will be crowded, this figure will be crowded. So let's draw a figure here. Let's keep that result here, and let's look at the angular momentum about the point B more closely. So this is our vertical, and this is our rod of length L. This angle is alpha, and this is the radius of the circular path. Okay. Now we have shown a direction for LB. See here, LB is perpendicular to LB is R cross MV. So LB is perpendicular to both RB and MV. Okay, it is in some direction. So let us look at this direction. Consider this direction is perpendicular to RB. So this is the direction of LB. Okay. Now what I am going to do is I am going to resolve this LB into two components. Okay, a horizontal component and a vertical component. This horizontal component let me call LR. Okay, because it's in the radial direction, and the vertical component let me call LZ because it is in the Z direction, vertical direction. This direction is taken as Z direction. Okay, so how do we resolve this? Suppose I extend this direction like this. Then if this is the vertical, then it's clear that this angle is alpha, because this okay, this angle is alpha, angle made by the rod with the vertical. Then naturally if you extend the direction of the rod, this angle between the direction of the rod and the vertical direction, it should be alpha. Okay, if this is alpha, then between LR and the direction of the rod, it must be 90 minus alpha. That means this direction must be, this angle must be alpha, because LB is perpendicular to the direction of the length of the rod. Okay, so we have this result. LR is nothing but LB cos alpha along the radial direction, and LZ is nothing but LB sin alpha along the k direction. Okay, so I have resolved LB into two components, radial component and a vertical component. Now what happens to these two components as the particle undergoes circular motion? Okay, this bob undergoes circular motion, right? This is the circular path. So as it undergoes circular motion, it's clear that even though the magnitude of LB, what is the magnitude of LB? See, we have calculated LB somewhere here. Look at equation 4. Magnitude of LB is mr omega L. All these terms are constant. So magnitude of LB must be constant. So as what happens to LB as this bob revolves around the circular path is, direction of LB will continuously change. That's clear, because LB is always perpendicular to RB and MB. Okay, so it will be perpendicular to the plane containing the length of the rod and the tangential momentum. Okay, so it will always be changing. The direction will always be changing. But when we look at this, each time we can resolve LB into a radial component and a vertical component. So which component will be changing? The direction of which component will be changing? It's clear that it will be the radial component which will be continuously changing. I mean, the direction of the radial component will be continuously changing. The direction of vertical component will remain the same. Okay, and the one reason is that there is no torque acting along the vertical direction. Okay, the only torque acting here is there is no torque along the vertical direction, so there won't be any change in the Z component of LB. Okay, so there won't be any change in the LZ or Z component of LB, but the radial component of LB will be continuously changing. Its direction will be continuously changing. Magnitude will not change, but the direction will change. Then what is the rate of change of the radial component? So when we try to calculate the rate of change of LB, we need to consider only the rate of change of the radial component, and that too the rate of change of the direction, right? So how do we express that? See, let us look at it like this. So I am considering this plane now. Okay, this circular plane. Okay, so this is the circle traced by the bob. Okay, let's assume that. Okay, now let us say this is I'm drawing it in a blown up fashion. This is the radial component at the time t. Okay, radial component should be perpendicular to the circle, and this is the radial component at the time t plus delta t. Okay, so this is the change. Let us call it delta LR, and this angle traced is delta theta within the time delta t. So when the delta t is very small, angle delta theta will be very small. So we can clearly show that, we can clearly write that delta LR, okay, is equal to, is approximately equal to LR into delta theta. Okay, so here the point is that the magnitude of LR is not changing because it is simply LB cos alpha. LB is a magnitude of LB is constant. We have seen that from equation 4. Okay, mr omega L, and cos alpha is also constant. So magnitude of LR is not changing, but only the direction is changing. So it's like the rotation of the vector LR. Okay, so within a small time delta t, the angle changed is delta theta, and delta theta will be very small when delta t is small. So we can approximately write this delta LR. We can take it as the arc length and radius into arc length, LR into delta theta. So let's divide both sides with delta t. So this is equal to LR delta theta by delta t, and let us take the limit delta t tends to 0. Limit delta t tends to 0. Then the left hand side becomes dLR by dt. Right side is LR into this becomes d theta by dt. But what is d theta by dt? It's nothing but the angular velocity omega, rate of change of angle. So dLR by dt is equal to LR into omega. In fact, this is a general expression. Okay, in general we can say that whenever a vector changes or rotates, its magnitude remains constant, only the direction changes. Okay, so then the only way you can change a vector in this fashion, that is magnitude, keeping the magnitude constant, only the direction is changed. The only possibility is rotation. When you rotate a vector like this, the rate of change of vector, rate of change of the magnitude of the vector, you can write as magnitude times omega. Okay, that is in general, the idea is in general, whenever we rotate a vector like this, we can write vector A, we are rotating like this, rate of change of the magnitude of the vector, we can write as A, magnitude of A into omega, something like this. Okay, this is what we are doing when we write, if it's a radial, consider uniform circular motion, then rate of change of the radial vector, magnitude of rate of change of radial vector, we write as R into omega. Okay, this is the basis of the equation. Magnitude of velocity, the linear velocity or tangential velocity is equal to R omega. Okay, so this is these are all special cases. So what we have written here, dLR by dt is equal to LR into omega, or in uniform circular motion, magnitude of V is equal to R omega. These are all special cases of this general relation. Rate of change, whenever a vector changes in direction only, magnitude remaining constant, rate of change of the magnitude of the vector we can write as the magnitude of the vector into omega, where omega is the angular velocity of this rotation. Okay, So let us try to use this result. Let me substitute for LR. So this is equal to, what is the expression for LR? From this figure, LR is equal to here. LR is equal to LB cos alpha, right? So let us substitute LB cos alpha into omega. But what was LB? What was the expression for LB? From equation 4, mr omega L, right? Okay, so let us substitute that here. So mr omega L into cos alpha into omega. Okay, so that's equal to mr omega square L into cos alpha. Let us try to again rewrite this slightly. This mr omega square here, this mr omega square, this is the expression for centripetal force, mv square by r. If we substitute v is equal to r omega, centripetal force is mr omega square. So mr omega square is nothing but the force acting towards the center. Okay, it is this force. What is the value of this force? We have seen that here. What is this force? It's nothing but T sine alpha. Okay, so the centripetal force, the force towards center, is nothing but T sine alpha. So let us substitute for mr omega square. Mr omega square is T sine alpha. Therefore, dlr by dt is equal to T sine alpha. I am substituting for mr omega square into L cos alpha. Okay. Again, we have used equation 2. See, in equation 2, instead of T cos alpha, I can substitute as mg. We have used it before also here. T cos alpha, we have substituted as mg. So here also, let us take this T from here. Let us take this cos alpha from here. That we can substitute as mg. So this we can rewrite as mgl sin alpha. Okay, this is the direction of dlr by dt. This is the magnitude of dlr by dt. Okay, now what is the direction of dlr by dt? From the figure it is clear that the direction of dlr by dt must be the same as the direction of delta lr. Okay, the rate of the change in LR. What is the direction of delta LR? It's the direction of increase of delta theta, that is theta cap direction. So I can write this as in the vector form, d by dt of LR is equal to mgl sin alpha theta cap. Okay, therefore I can write d by dt of LB, because in LB, the angular momentum of this bob about the point B, what was our figure here? In LB, the only change in LB comes from the radial factor LR. LZ remains constant. Okay, so dLR by dt is same as dLB by dt. LZ is a constant. If I simply write, see, if I write it here, if I write LB as LR plus LZ, this LZ is a constant, so dLB by dt is same as dLR by dt. The only change in LB comes from the rate of change of radial part, and that too rate of change of the direction of the radial part. Okay, therefore I can finalize this as the rate of change of LB is equal to mgl sin alpha along theta cap direction. What is this equation? Next number, equation 6. Look at equation 5 now. What is equation 5? Torque on the bob about the point B is mgl sin alpha theta cap. Look at the right hand side of equation 6, mgl sin alpha theta cap. Okay. So it means that this d by d, left hand side also should be the same. D by dt of LB should be same as torque acting at the point B. So we have established this result from equation 5 and 6. We get d by dt of angular momentum, rate of change of angular momentum of the bob about the point B is equal to torque about the point B. So in the case of conical pendulum, we have considered the rate of change of angular both origins. Okay, origin A. Here the situation is that angular momentum is a constant, and we have shown that torque is 0. Torque is 0 about this point. When torque is 0, angular momentum, we get angular momentum constant. So this indicates that the relationship between torque and angular momentum must be like this. Torque is equal to dl by dt. This verifies that. And about origin B also, we have established now first angular momentum we have calculated, okay, and then we calculated torque about point B, which is mgl sin alpha theta cap direction, okay, tangential to the circular path. Then we calculated the rate of change of LB. We have seen that in LB there are two components, a radial component and a vertical Z component. Vertical component does not change. Because there is no torque along the, there is no net force along the vertical direction. Okay, there is also no torque along the vertical direction, so there is no change. In order for a change in angular momentum, there should be some torque. So there is no torque along the vertical direction. So there is no change in angular momentum along the vertical direction. So Lz is a constant, only Lr changes, and even the magnitude of Lr remains constant, which is Lb cos alpha, only the direction of Lr changes. So in order to change the direction of a vector, we have to rotate the vector. Then the rate of change of vector we can express as the magnitude of the vector into omega, which is a general relationship. Okay, and finally we have shown that the rate of change of Lb is equal to mgl sin alpha along theta cap direction. In other words, the rate of change of LB is same as torque. Okay, so this result we have established for conical pendulum also.